Have you ever looked up at the night sky and wondered what lies beyond our cosmic neighborhood? What secrets do those distant points of light hold? Today, we're going to explore one of the most humbling realities of our existence. Why reaching even our closest stellar neighbor might be an impossible dream. And here is a question for you. If you could break one law of physics for a day, which would it be, and what would you do? Share your wildest idea in the comments. I will pin the most creative answer. Now let's begin. When you gaze toward the constellation Centaurus, visible only from Earth's southern hemisphere, you're actually looking at a triple star system called Alpha Centauri. It's made up of two sun-like stars dancing around each other, called Alpha Centauri A and Alpha Centauri B, plus a small red dwarf named Proxima Centauri. This tiny crimson star, Proxima, holds the record as the closest stellar neighbor to our Sun. It sits just 4.24 light-years away from us. Now, 4.24 light-years might sound like a relatively short distance when you say it out loud. After all, it's our nearest star. How hard could it be? But here's where things get sobering. A light-year represents the distance that light itself travels in an entire year, moving at roughly 186,282 miles per second. When you do the mathematics, one light-year equals about 5.88 trillion miles, or 9.46 trillion kilometers. Multiply that by 4.24, and you're looking at approximately 25 trillion miles, or roughly 40 trillion kilometers, separating us from our nearest stellar neighbor. Let me put this into perspective that makes the scale truly hit home. Remember the Voyager 1 spacecraft? Launched back in 1977, it's currently the most distant human-made object in existence. This remarkable probe has been traveling through space for nearly 5 decades, moving at approximately 38,000 miles per hour relative to the Sun. That might sound incredibly fast, and by our everyday standards, it absolutely is. But at that velocity, Voyager 1 would need more than 70,000 years to reach Proxima Centauri. Think about that for a moment. 70,000 years ago, modern humans were just beginning to migrate across the globe. The pyramids wouldn't be built for another 67,000 years. The entire span of recorded human history, from the first civilizations to today, represents less than 10% of the time it would take Voyager to reach our nearest star. But technology advances, right? Perhaps we could build something faster. NASA's Parker Solar Probe, launched in 2018, currently holds the record as the fastest spacecraft ever built by humanity. During its closest approaches to the Sun, this remarkable vehicle reaches speeds of approximately 430,000 miles per hour. That's more than 10 times faster than Voyager 1. Surely that makes a difference. Well, yes, but perhaps not as much as you'd hope. Even at these blistering speeds, the Parker Solar Probe would still require roughly 25,000 years to reach Proxima Centauri. We've improved the travel time by a factor of nearly 3, yet we're still talking about a journey spanning more than 250 centuries. Now let's imagine we poured unlimited resources into developing the most advanced propulsion systems that current physics allows. Chemical rockets, the kind that have taken us to the moon and powered every human spaceflight mission to date, are fundamentally limited by how much energy you can extract from chemical reactions. Even with perfect efficiency, which is physically impossible, they simply cannot provide enough thrust to reach the speeds necessary for practical interstellar travel within a human lifetime, or even within many human lifetimes. What about nuclear propulsion? Engineers have proposed various concepts using nuclear reactions to power spacecraft. Nuclear fission, the process that powers our current nuclear reactors and submarines, could theoretically propel a spacecraft to perhaps 3 to 5% of light speed. At 5% of light speed, you'd still need roughly 85 years to reach Proxima Centauri. That's better, significantly better, but it's still longer than most human lifespans. You'd need to send crew members who would spend their entire lives aboard the vessel, perhaps even requiring multiple generations to complete the journey. If you're enjoying this deep dive into the cosmos and want to stay connected with the latest discoveries that shape our understanding of space, don't forget to hit that subscribe button and give this video a like. Your help tells me you're finding value in this content, and it helps others discover these cosmic mysteries too. Nuclear fusion, the process that powers the sun itself, offers even more promise. Fusion rockets could theoretically achieve 10 to 15% of light speed, cutting the travel time to Proxima Centauri down to somewhere between 28 and 42 years. Now we're talking about a journey that could potentially occur within a single human lifetime. But here's the challenge. We still haven't achieved controlled nuclear fusion on Earth, despite decades of research and billions of dollars invested. The International Thermonuclear Experimental Reactor, or ITER, currently under construction in France, represents humanity's best attempt at creating sustained fusion reactions. If successful, it will generate its first plasma sometime around 2025 or 2026. But that's just the beginning. Going from a massive experimental facility on Earth to a compact, efficient fusion drive capable of powering an interstellar spacecraft is an engineering challenge of staggering proportions. The distances involved aren't the only problem, though they're certainly the most obvious one. Even if we somehow develop propulsion technology capable of reaching, say, 20% of light speed, the journey itself presents obstacles that sound like they're pulled straight from science fiction, except they're very real physics. At 20% of light speed, you're moving at roughly 134 million miles per hour. At these velocities, even a grain of dust becomes a potentially catastrophic threat. The kinetic energy of a collision increases with the square of velocity, meaning that doubling your speed doesn't just double the impact energy, it quadruples it. A single grain of sand weighing perhaps 1 milligram hitting your spacecraft at 20% of light speed would release energy equivalent to roughly 15 kilograms of TNT exploding. That's enough to punch clean through any material we currently know how to manufacture. The space between stars, called the interstellar medium, isn't perfectly empty. It contains roughly 1 atom per cubic centimeter on average, mostly hydrogen, along with occasional dust grains and larger particles. This might sound incredibly sparse. After all, the best vacuum we can create on Earth still contains billions of particles per cubic centimeter. But when you're traveling across distances measured in trillions of miles, even this incredibly diffuse medium becomes a serious hazard. Your spacecraft would be constantly bombarded by particles, each one hitting with tremendous energy. Over the course of a decades-long journey, this cumulative damage could be catastrophic. Engineers have proposed various solutions: massive shields at the front of the spacecraft, electromagnetic deflectors to push charged particles aside, or perhaps clouds of dust deployed ahead of the vehicle to vaporize incoming material before it can hit critical systems. Each solution adds mass, complexity, and points of potential failure to an already incredibly ambitious mission. Then there's radiation. Space beyond Earth's protective magnetic field is flooded with cosmic rays. High-energy particles accelerated to nearly light speed by supernovae, active galactic nuclei, and other violent cosmic events. These particles can penetrate deep into matter, damaging electronics and biological tissue alike. On the International Space Station, astronauts are protected by Earth's magnetosphere for much of their orbit. On a journey to Mars, lasting 6 to 9 months, radiation exposure is a serious concern that mission planners are still working to address. On a multi-decade voyage to another star system, crew members would accumulate radiation doses far beyond anything humans have ever experienced. The shielding required to protect them would add enormous mass to the spacecraft, making it even harder to accelerate to the necessary speeds. Let's talk about something that might offer hope: the Breakthrough Starshot initiative. Announced in 2016 by entrepreneur Yuri Milner, the late physicist Stephen Hawking, and a coalition of visionary scientists, this project proposed something radical. Instead of building massive spacecraft with enormous fuel reserves, what if we made our probes incredibly small? What if we made them so light that we could push them using nothing but focused beams of light? The concept sounds almost magical. Imagine a spacecraft no bigger than a microchip, weighing just a few grams, attached to an ultra-thin reflective sail perhaps 4 meters wide. Now picture an array of powerful lasers on Earth's surface, all focused on this tiny sail, firing photons that transfer their momentum to the craft. Light has no mass, but it does carry momentum. When photons bounce off the reflective sail, they push it forward, gradually accelerating the tiny spacecraft to astonishing velocities. The numbers are genuinely impressive. Breakthrough Starshot aimed to accelerate these starships to approximately 20% of light speed. At that velocity, a probe could reach the Alpha Centauri system in just over 20 years, plus another 4.24 years for its signals to return to Earth. Within a single human generation, we could potentially have photographs and scientific data from another star system. It's a breathtaking vision, one that transforms interstellar exploration from a multi-millennial endeavor into something we might actually witness in our lifetimes. But here's where reality intrudes on the dream. Despite the initial $100 million pledge that launched Breakthrough Starshot with tremendous fanfare, the project has quietly faded. Public accounting suggests less than $10 million was actually spent. Philip Lubin at the University of California, Santa Barbara, one of the leading researchers in laser propulsion, received approximately $200,000 over 8 years from the initiative, actually less than his NASA grants for similar work. Activity peaked between 2020 and 2021, with large group meetings identifying key obstacles and issuing small grants. But in the last couple of years, funding dried up, meetings ceased, and communications quietly disappeared. What happened? The initiative did accomplish something valuable. It normalized interstellar travel as a feasible goal and brought attention to concepts that had been relegated to the fringes of aerospace engineering. But it also revealed that the cost would be far, far more than $100 million. The engineering challenges aren't just difficult, they border on the impossible with current technology. Consider what you'd actually need to make this work. First, the laser array. We're not talking about a few powerful lasers. The system would require an array capable of generating approximately 100 gigawatts of optical power. That's roughly 100 times the output of a typical nuclear power plant, focused with incredible precision on a 4-meter sail that's rapidly accelerating away from Earth. The array would need to track the spacecraft with extraordinary accuracy as it speeds up, maintaining focus on a target that's getting smaller and more distant with each passing second. Any misalignment, even by a fraction of a degree, and the laser beam misses entirely, wasting enormous amounts of energy. The acceleration phase would last perhaps 10 minutes, during which the starship would experience forces of roughly 40,000 times Earth's gravity. That's 40,000 Gs. For comparison, the Space Shuttle astronauts experienced about 3 Gs during launch. Fighter pilots can briefly withstand 9 Gs with special suits. 40,000 Gs would instantly pulverize any human body, but even for electronics, this presents extraordinary challenges. Every component, every circuit, every connection must be designed to withstand these crushing forces without failing. Speaking of the sail itself, researchers at Caltech, including Harry Atwater's team, explored materials like silicon nitride for ultra-thin sails capable of enduring both the 40,000 G acceleration and 100 gigawatts of laser power focused on a few square meters. They created small-scale prototypes showing promise, but building a full sail that meets all these requirements simultaneously? That's a materials science challenge, unlike anything we've attempted before. If you found that fascinating and want to explore more about the possibilities and limitations of interstellar travel, I have another video diving deep into the physics of faster-than-light concepts. It's called Will We Ever Achieve Faster-Than-Light Travel?, where we explore warp drives, wormholes, and what Einstein's relativity really tells us about the cosmic speed limit. You'll find it linked in the description and in the cards above. Trust me, if this topic captivates you, that video will blow your mind. Now let's assume for a moment that we solve all these engineering challenges. We build the laser array, perfect the sail material, and successfully accelerate our gram-scale probe to 20% of light speed. The probe is now hurtling through interstellar space at 134 million miles per hour. What happens next? Remember those dust grains we discussed earlier? At 20% of light speed, even microscopic particles become devastating projectiles. The Starship design includes no room for massive shielding. The entire point is to keep the mass as low as possible. Some proposals suggest deploying a small cloud of sacrificial material ahead of the probe to vaporize incoming particles before they can damage critical systems, but this adds complexity and mass. Others propose using the sail itself as a shield, positioning it to protect the delicate electronics behind it. But the sail must remain intact for potential braking maneuvers near the destination, and any damage accumulates over the 20-plus-year journey. Then there's the communication challenge, which might be the most overlooked aspect of the entire mission. Imagine you're the Starship, now 4 light-years from Earth, having just completed your flyby of Proxima Centauri. You've captured images, collected data on magnetic fields, analyzed the composition of any planets in the system. You need to send this information home, but you're a device weighing a few grams, powered by a tiny battery, or perhaps a microscopic radioactive power source, and you need to transmit a signal across 4.24 light-years of space with enough strength that receivers on Earth can detect it. Radio signals, like all electromagnetic radiation, follow the inverse square law. This means that as your signal spreads out through space, its intensity decreases proportional to the square of the distance. Double the distance, and the signal becomes 4 times weaker. Quadruple the distance, and it becomes 16 times weaker. Across 4.24 light-years, your signal is spread incredibly thin. The power required to send a detectable signal across that distance from a gram-scale transmitter is enormous, potentially requiring most or all of the probe's power reserves. And remember, at 20% of light speed, with no method to slow down, your flyby of the target system is brief, perhaps just a few hours or even minutes to collect all your data before you sail past and continue into the cosmic void forever. These aren't insurmountable problems in the sense that they violate the laws of physics. They're just extraordinarily difficult engineering challenges that require breakthroughs in multiple fields simultaneously: materials, science, laser technology, miniaturized electronics, power storage, and communication systems. The $100 million initially pledged to break through Starshot was, in hindsight, a down payment on preliminary research into these challenges. Actually building and launching such a mission? The realistic cost estimates run into tens of billions of dollars, possibly hundreds of billions, rivaling or exceeding the entire budget of programs like the International Space Station or the James Webb Space Telescope. But let's dream even bigger. Suppose we set aside the cost concerns. Imagine that humanity collectively decides this is a priority and commits whatever resources are necessary. We solve the engineering challenges, build the infrastructure, and successfully send our first Starship to Alpha Centauri. 20 years pass, then 4.24 more years as the signals crawl back to Earth at light speed. Finally, on a day nearly a quarter century after launch, the first images and data from another star system arrive. It would be, without question, one of the greatest achievements in human history, a moment comparable to the first photographs from the surface of Mars or the iconic Earthrise image captured by Apollo 8. Yet even in this optimistic scenario, we haven't reached another star. We've sent a flyby probe, a tiny robotic emissary that collects a snapshot during a brief passage and then continues into the darkness. There's no orbiting, no landing, no detailed long-term study, and certainly no human presence. The information we receive is limited by what a gram-scale probe can carry and transmit across trillions of miles. Now let's confront an even more fundamental barrier, one that doesn't depend on engineering prowess, or technological innovation. This obstacle is woven into the very fabric of reality itself, the speed of light, and Einstein's theory of special relativity. In 1905, Albert Einstein published a paper that revolutionized our understanding of space and time. Special relativity revealed that the speed of light in a vacuum, approximately 186,282 miles per second, isn't just a really fast speed, it's a cosmic speed limit, an absolute boundary that nothing with mass can ever reach, let alone exceed. Why is this? The mathematics might seem abstract, but the physical consequences are profound. As an object with mass accelerates closer to light speed, several strange things happen. First, its mass effectively increases. This doesn't mean the object gains matter, rather, it becomes increasingly difficult to accelerate further. The energy required to push it faster grows exponentially. To accelerate a spacecraft with even modest mass, say 1 ton, to 90% of light speed would require energy equivalent to the entire annual power output of human civilization. To reach 99% of light speed would require far more. To actually reach 100%, the energy requirement becomes infinite. Not just really large, actually infinite. It's not a technological limitation, it's a fundamental law of the universe. Second, time itself behaves strangely at relativistic speeds. From the perspective of someone on the spacecraft traveling at a significant fraction of light speed, time passes normally. You'd age normally, eat your meals, go about your routine, but relative to people back on Earth, your clock is running slower. At 90% of light speed, for every year you experience, about 2.3 years pass on Earth. At 99% of light speed, every year aboard the ship corresponds to roughly 7 years back home. This effect, called time dilation, has been confirmed countless times in particle accelerators and precise atomic clock experiments. For a human crew traveling to Proxima Centauri at, say, 80% of light speed, the journey might feel like only 3 years in each direction. But due to the distance involved and the speed limit of light, observers on Earth would measure the journey as taking over 5 years each way, plus the time for signals to return. The travelers would return having aged 6 years, but Earth would have aged over a decade, not counting the years needed to accelerate and decelerate. Their friends, family, and the world they knew would have moved on without them. Every interstellar journey becomes a one-way trip through time, even if you physically return. Third, there's the problem of actually stopping once you arrive. Getting up to relativistic speeds is extraordinarily difficult, but slowing down again might be even harder. You can't just fire your rockets in reverse, you'd need to carry enough fuel to decelerate, which means carrying that fuel during the acceleration phase, which means you need even more energy to get started. The fuel requirements grow exponentially, a problem engineers call the tyranny of the rocket equation. Some proposals suggest using the destination star itself to slow down. You could deploy a sail and use the stellar wind and radiation pressure from Proxima Centauri to brake. But Proxima is a red dwarf, much dimmer and cooler than our Sun, producing far less radiation. The deceleration would be gentle, possibly taking years, during which you'd overshoot your target and need to loop back. Other concepts involve magnetic sails that interact with the stellar magnetic field, but again, this requires the spacecraft to carry additional equipment, adding mass and complexity. Let me share something that might sound encouraging at first, but actually highlights how trapped we are by physics. In 2025, NASA's James Webb Space Telescope found strong evidence of a giant planet orbiting Alpha Centauri A, one of the 2 Sun-like stars in the system. This discovery, made using the telescope's mid-infrared instrument, represents a planet much closer than the over 4 light-years to Proxima Centauri. It's in a system just 4.37 light-years away. At first glance, that difference seems trivial, but remember, we're talking about distances where even tiny fractions of a light-year represent trillions of additional miles. Whether we're discussing 4.24 light-years or 4.37 light-years, the fundamental impossibility remains unchanged. These are distances that mock our current capabilities. Here's another sobering realization. Even if we achieved what seems impossible, traveling at 99% of light speed, the journey to Proxima Centauri would still take over 4 years as measured from Earth, plus the years to accelerate and decelerate. Compare this to every other exploratory mission humanity has undertaken. The Polynesians who settled the Pacific Islands could complete their voyages within months. The European age of exploration saw ships return from around the world within years. The Apollo missions to the Moon took days. Even a mission to Mars, the next great goal of human spaceflight, would take 6 to 9 months each way with current propulsion technology, with total mission durations of 2 to 3 years, including surface time. Interstellar distances operate on an entirely different scale. The nearest star is nearly 10,000 times more distant than the nearest planet beyond Earth. This isn't like crossing an ocean versus crossing a continent. This is like comparing a stroll around your neighborhood to a journey that would circle Earth's equator thousands of times. The scale doesn't just make interstellar travel difficult, it fundamentally changes the nature of what's possible. Consider the practical implications for human crews. A journey taking decades means you're not sending explorers, you're sending colonists who will spend their entire lives in transit, possibly never reaching the destination themselves. The concept of generation ships has been explored in science fiction for decades. Massive vessels that sustain populations across multiple generations, with the descendants of the original crew finally arriving at the destination star centuries after departure. But generation ships introduce problems that go far beyond engineering. How do you maintain social cohesion across multiple generations of people born in space who've never seen Earth and never will? How do you preserve knowledge, culture, and mission purpose over centuries? What happens if social structures break down, if future generations decide they no longer want to continue the mission, or if technical problems accumulate over decades until the ship becomes uninhabitable? And perhaps most troubling, who has the right to condemn children not yet born to spend their entire lives aboard a spacecraft bound for a destination they didn't choose? Zach Manchester at Carnegie Mellon University worked on ChipSats, tiny satellites launched to Earth orbit, as prototypes for breakthrough Starshot's nanocrafts. These represent one approach to the problem: send tiny robotic probes instead of humans. No life support, no food, no psychological concerns about isolation and confinement. Just miniaturized science instruments and cameras collecting data and sending it home. But this sidesteps rather than solves the fundamental question we're exploring. When people dream of reaching the stars, they're not usually imagining tiny robots taking pictures. They're imagining humans walking on alien worlds, establishing new homes among the stars, becoming an interstellar species. That dream, as beautiful and inspiring as it is, crashes against the immovable wall of physics. The speed of light isn't a technological barrier waiting to be overcome with clever engineering. It's baked into the structure of space-time itself, linked fundamentally to causality, the principle that causes precede effects. If you could travel faster than light, you could, in principle, arrive before you left, creating paradoxes that would violate the most basic logical consistency of the universe. Some physicists have explored theoretical loopholes. What about wormholes, tunnels through space-time that connect distant points? The mathematics of general relativity allows for them, but only if you have exotic matter with negative energy density, something we've never observed and may not exist. What about warp drives, where you contract space in front of your ship and expand it behind, surfing on a wave of space-time itself? Again, the equations permit this under certain conditions, but those conditions require amounts of energy equivalent to the mass energy of entire planets or even stars, along with that same exotic matter. These concepts remain firmly in the realm of speculation, interesting as thought experiments but offering no practical path forward with anything resembling current or near-future technology. Let's explore what happens when we try to think outside conventional propulsion entirely. If chemical rockets, nuclear engines, and even laser-pushed sails can't practically get us to another star within a human lifetime, what other options exist? Scientists have proposed some genuinely creative approaches, each revealing new aspects of just how trapped we are by the laws of physics. One concept that periodically resurfaces is antimatter propulsion. When matter meets antimatter, they annihilate each other completely, converting 100% of their mass into pure energy according to Einstein's famous equation, E equals mc squared. No other reaction in the universe is more efficient. A single kilogram of antimatter reacting with a kilogram of matter releases energy equivalent to approximately 43 megatons of TNT, roughly the yield of the largest thermonuclear weapons ever tested. Channeled properly, this energy could theoretically accelerate a spacecraft to a substantial fraction of light speed. The concept sounds perfect until you examine the practical challenges. First, antimatter doesn't exist naturally in accessible quantities anywhere in our solar system. Every atom of antimatter must be manufactured in particle accelerators, and current facilities produce antimatter, literally atom by atom. CERN, home to the Large Hadron Collider, produces perhaps a few nanograms of antiprotons per year. To fuel an interstellar spacecraft would require milligrams or even grams of antimatter, quantities millions or billions of times greater than humanity's entire production to date. The energy cost of producing antimatter far exceeds the energy you get back from annihilating it, making it a storage medium rather than a power source. Second, storing antimatter presents nightmarish challenges. The instant antimatter touches ordinary matter, it annihilates, releasing that tremendous energy. You can't store it in any normal container. The only methods involve magnetic or electric fields strong enough to levitate antimatter particles away from the container walls, systems that require continuous power and perfect reliability. A single failure, a momentary power interruption, and your entire antimatter fuel supply annihilates in a catastrophic explosion that makes nuclear weapons look gentle by comparison. Despite these obstacles, let's imagine we somehow solve the production and storage problems. An antimatter-powered spacecraft could theoretically reach perhaps 40 to 50% of light speed, cutting the journey to Proxima Centauri to roughly 10 years. That's genuinely impressive, entering the realm where a single human lifetime could complete a round trip. But we're still talking about decades of travel through the hostile interstellar medium, decades during which any system failure could be fatal, and decades during which the crew ages while Earth continues advancing. The astronauts who return after 20 or 25 years would find themselves in a world that's moved on, potentially with technology that makes their heroic journey seem quaint. Another proposal involves something called a Bussard ramjet, named after physicist Robert Bussard, who conceived the idea in 1960. Picture a spacecraft with an enormous magnetic scoop extending ahead of it, perhaps thousands of kilometers across. As the ship moves through interstellar space, this scoop funnels hydrogen atoms from the interstellar medium into a fusion reactor. The ship essentially scoops up its fuel as it goes, eliminating the need to carry massive fuel reserves. In theory, such a craft could continuously accelerate, potentially reaching relativistic speeds limited only by the efficiency of the fusion process and the drag created by the magnetic field interacting with the interstellar medium. It's an elegant concept, but the challenges are formidable. First, you need a functioning fusion reactor, which we still haven't achieved on Earth. Second, the interstellar medium is incredibly sparse, roughly 1 atom per cubic centimeter on average. To gather meaningful amounts of hydrogen, your magnetic scoop must be truly enormous, extending across volumes of space comparable to planetary orbits. Third, the energy required to maintain such a powerful magnetic field might exceed the energy you gain from the collected fuel, especially at lower speeds when you're not yet moving fast enough to scoop up large quantities. Fourth, The drag from that same magnetic field interacting with the interstellar medium creates resistance that works against your acceleration. Detailed analyses suggest that a Bussard ramjet might actually decelerate at high speeds rather than continue accelerating, defeating the entire purpose. What about using the environment itself more cleverly? One proposal suggests magnetic sails, large loops of superconducting wire that generate powerful magnetic fields. These fields interact with stellar winds, the streams of charged particles flowing outward from stars, and with the galactic magnetic field permeating interstellar space. Unlike physical sails that catch photons, magnetic sails push against charged particles. Near a star, they could provide thrust for departure. In deep space, they could potentially provide gentle, continuous acceleration by interacting with the galaxy's magnetic field. Some optimistic estimates suggest travel times to Proxima Centauri could be reduced to perhaps 10 to 15 years. However, the galactic magnetic field is extraordinarily weak, and the thrust provided would be minuscule. You'd need a magnetic sail stretching across hundreds of kilometers to generate meaningful acceleration, and you'd need superconducting materials that maintain their properties for decades in the harsh environment of space. The technology is theoretically possible, but the engineering requirements push the boundaries of what we can envision building, even with generous assumptions about future technological advancement. Here's a concept that sounds like pure science fiction but is grounded in real physics, using black holes. Not flying into them, obviously, but using their intense gravitational fields for something called a gravitational slingshot, taken to an extreme level. When a spacecraft passes close to a massive object, it can steal a tiny bit of that object's orbital momentum, accelerating in the process. We use this technique routinely with planets. The Voyager spacecraft gained tremendous speed through flybys of Jupiter and Saturn. But black holes, with their intense gravitational fields compressed into tiny regions, could theoretically provide far more dramatic boosts. A spacecraft that skimmed the event horizon of a rotating black hole, following a carefully calculated trajectory, could potentially emerge, traveling at a significant fraction of light speed. The physics works in principle. The practical problems are, well, astronomical. The nearest known black hole to Earth is about 1,500 light-years away, over 300 times more distant than Proxima Centauri. You'd need to travel an immense distance just to reach your gravity assist, which you'd then use to travel to your actual destination. It's like proposing to solve the problem of crossing a stream by first building a bridge across an ocean. Additionally, the tidal forces near a black hole's event horizon would rip any known spacecraft apart unless you used a truly massive black hole, which generates weaker tidal forces at its event horizon, but also provides a less dramatic gravitational assist. Every alternative propulsion concept humanity has devised eventually collides with one or more insurmountable barriers. Either the physics doesn't work as hoped, or the engineering requirements exceed anything we can realistically build, or the energy costs are prohibitive, or the timescales remain stubbornly long. It's not that we lack imagination or ambition, it's that the universe has rules, and those rules don't care about our aspirations. Let me share something that really drives this home. In 2024, NASA selected a proposal called Swarming Proxima Centauri for Phase 1 development as part of the NASA Innovative Advanced Concepts program. Led by Marshall Eubanks at Space Initiatives Incorporated, working with the Initiative for Interstellar Studies, this concept builds on the breakthrough Starshot idea, but acknowledges the brutal reality that a single gram-scale probe would be incredibly vulnerable and limited. Instead, the proposal envisions sending a swarm of tiny probes, each carrying different instruments, providing redundancy and more comprehensive data collection. It's a clever approach that addresses some of the vulnerabilities of single-probe missions. If one probe is destroyed by dust impacts, others continue. If one probe's communication system fails, others can relay the data. The swarm could potentially map out multiple objects in the target system during their brief flyby. But notice what hasn't changed. These are still gram-scale probes, still moving at a fraction of light speed, still facing all the same fundamental challenges we've discussed. The swarm concept improves reliability and data quality, but it doesn't solve the underlying problem that we're sending tiny robots on multi-decade journeys across distances that dwarf anything in human experience, with no possibility of human presence, no chance to stop and explore, no opportunity to truly reach another star in any meaningful sense. There's another aspect of interstellar travel we need to confront, one that's less about physics and more about biology and psychology. Even if we solved every propulsion challenge, even if we found a way to reach 20 or 30% of light speed, we'd still face the profound difficulties of keeping humans alive and sane during voyages lasting decades or longer. Let's start with the most basic requirement: sustaining human life. The International Space Station, our most advanced and long-lasting outpost beyond Earth, operates only because we constantly resupply it. Every few months, cargo spacecraft arrive carrying food, water, spare parts, scientific equipment, and other necessities. The station does recycle water with impressive efficiency. Roughly 93% of water is recovered from humidity, urine, and other sources. But complete closure of life support systems where absolutely everything is recycled indefinitely remains beyond our current capabilities. There's always some loss, always some need for resupply. On a journey to another star, resupply is impossible. Once you leave Earth's vicinity, you're on your own for decades. Every molecule of oxygen, every drop of water, every calorie of nutrition must either be carried from the start or regenerated from waste products. The life support systems must achieve near-perfect efficiency, recycling essentially everything with minimal losses, because there's nowhere to obtain replacements. Plants might help. Photosynthesis converts carbon dioxide back to oxygen while producing edible biomass. But growing enough plants to sustain a crew requires significant space, powerful lighting, careful temperature and humidity control, and protection from radiation. The mass budget for an interstellar spacecraft would need to include not just the crew compartment, but essentially a miniature biosphere, a self-contained ecosystem capable of functioning flawlessly for decades. And here's a troubling reality. Ecosystems are complex, dynamic systems prone to unexpected fluctuations and collapses. On Earth, if crops fail in one region, we import food from elsewhere. If a disease devastates one population, species migrate in from surrounding areas. On a spacecraft, the entire ecosystem exists within a rigid container hurtling through space. There's no external buffer, no safety margin. If something goes wrong, if a disease wipes out a crucial plant species, if microbial populations drift away from their optimal balance, if any of countless possible failures occur, the crew faces potential starvation or suffocation with no possibility of rescue or resupply. Then there's radiation, a threat we've mentioned before but deserves deeper examination. Beyond Earth's protective magnetic field, space is flooded with radiation from multiple sources. Solar flares unleash bursts of high-energy particles, galactic cosmic rays, accelerated by distant supernovae and other violent events, permeate interstellar space with particles moving at nearly light speed. These cosmic rays can penetrate deep into matter, passing through spacecraft hulls and human bodies alike. The effects are cumulative and devastating. Radiation damages DNA, increasing cancer risks dramatically. It can cause cataracts, cardiovascular disease, and central nervous system damage. High doses lead to acute radiation sickness, nausea, weakness, hair loss, immune system collapse, and potentially death. Astronauts on the International Space Station, protected partly by Earth's magnetosphere, receive radiation doses roughly equivalent to 8 chest X-rays per day. On an interstellar journey far from any protective magnetic field, the exposure would be orders of magnitude higher. Shielding helps, but it adds tremendous mass. The most effective shielding materials are dense elements like lead or, surprisingly, hydrogen-rich compounds like water and plastics. Water serves double duty. It's necessary for life support and provides radiation protection. but the amount needed to shield a crew compartment adequately adds tons of mass to the spacecraft, mass that must be accelerated to interstellar velocities at enormous energy cost. Some designs propose surrounding crew quarters with water tanks and food storage, using necessary supplies as radiation shields. But as supplies are consumed during the voyage, radiation protection decreases, meaning crew exposure increases over time precisely when they're most exhausted and vulnerable. There's also psychological isolation to consider, an aspect that's harder to quantify than radiation doses or calorie requirements, but potentially just as mission critical. Antarctic research stations provide some insight. Scientists who winter over at places like the South Pole Station spend months isolated in small groups in harsh conditions with no possibility of leaving until seasonal weather permits resupply flights. Even with modern communications technology, satellite internet, and video calls to loved ones back home, crew members report significant psychological stress, anxiety, depression, interpersonal conflicts, and cognitive decline. Now amplify that isolation dramatically. An interstellar crew wouldn't be months from help, they'd be years or decades away. Communication with Earth would be increasingly delayed as the light speed gap widened. After 1 year of travel at 20% of light speed, you're roughly 0.2 light-years from Earth, meaning radio messages take 2.5 months each way, 5 months between sending a message and receiving a reply. 10 years into the journey, communication delays stretch to 2 years. You send a message and by the time the reply arrives, the situation has likely changed dramatically. Real-time conversation becomes impossible. You're functionally alone, more isolated than any human has ever been. The crew would inevitably develop their own culture, their own ways of resolving conflicts, their own priorities that might drift away from the mission planner's intentions. What happens when someone becomes seriously mentally ill, a danger to themselves or others? On Earth, we have psychiatric hospitals, medications, therapies, and if necessary, physical restraints and isolation. On a spacecraft, options are extremely limited. You can't send someone home. You can't bring in outside specialists. The small crew must handle everything internally, and if social cohesion breaks down, if factions develop, if violence erupts, there's no authority to appeal to, no escape, nowhere to go. Some proposals suggest suspended animation or hibernation, putting crew members into a state of reduced metabolism where they sleep through most of the journey, awakening only near the destination. This would reduce life support requirements, minimize psychological stress, and reduce radiation exposure by allowing more of the spacecraft's mass to be dedicated to shielding. It sounds ideal, but we have no proven technology for long-term human hibernation. Bears hibernate for months, but they're adapted for it through millions of years of evolution. Humans put into medically induced comas for more than a few weeks face serious complications: muscle atrophy, bone loss, immune system dysfunction, bed sores, and infection risks. Research continues into hibernation-like states for space travel, but we're far from anything reliable. Even if we developed such technology, would you volunteer to be unconscious for 20 years, trusting that the automated systems will wake you successfully, that nothing will go wrong during your decades of vulnerability? Would you accept the risk that you might never wake up, or wake up to find the mission has failed, the spacecraft crippled, your crewmates dead, and yourself alone in the darkness between stars? Let me put this in perspective with actual numbers from recent proposals. A paper from Virginia Tech by aerospace engineer Amelie Lutz outlined a theoretical mission to Proxima Centauri b using fusion-powered propulsion. Under optimistic assumptions about fusion drive performance, the spacecraft might reach speeds allowing a journey of 40 to 50 years. That's within a single human lifetime, barely if crew members launched in their 20s or 30s. But the spacecraft itself would need to mass thousands of tons to include all necessary life support, radiation shielding, redundant systems, repair equipment, and consumables. Accelerating thousands of tons to even 10% of light speed requires energy measured in thousands of terajoules, energy equivalent to dozens of large nuclear weapons. The technological and economic barriers aren't just high, they're compounding. Every problem you solve creates new problems. Add more shielding and you need more energy to accelerate it. Add more fuel and you need even more fuel to accelerate that fuel. Increase the crew's size for redundancy and social health, and life support requirements multiply. Send more automated backups and spare parts, and mass increases further. The spacecraft grows larger, heavier, more expensive, and harder to accelerate with each improvement you attempt. Now let's examine what awaits us, even if we somehow overcome every obstacle we've discussed so far. Suppose we build the spacecraft, solve the propulsion challenges, protect the crew from radiation, maintain life support for decades, preserve psychological health, and successfully travel across light years of space. What happens when we actually arrive at another star system? The challenges don't end. In many ways, they intensify. First, there's the deceleration problem we touched on earlier, but it deserves fuller exploration. If you've accelerated to 20% of light speed, you're moving at roughly 134 million miles per hour. At that velocity, you cross the distance from Earth to the Sun, 93 million miles, in about 42 minutes. The entire inner solar system from the Sun out to Mars becomes a blur you traverse in hours. If you don't slow down, you'll scream through the Proxima Centauri system in a matter of days, perhaps catching a few hurried observations before you're past the star and its planets, continuing into interstellar space with no way to return. Slowing down requires energy equivalent to what you spent speeding up, assuming similar efficiency. If you carried fuel for deceleration, you had to accelerate that fuel during the first phase of your journey, dramatically increasing energy requirements. The rocket equation is merciless. Every kilogram of payload you want to decelerate requires multiple kilograms of fuel, which themselves required even more fuel to accelerate initially. The mass ratios become absurd very quickly. Alternative deceleration methods exist in theory. You could deploy a large sail and use radiation pressure from the destination star to gradually slow down. But Proxima Centauri is a red dwarf, producing far less radiation than our Sun. The deceleration would be slow, taking years, during which you'd overshoot your target by enormous distances and need to loop back. Or you could use a magnetic sail dragging against the stellar wind and the star's magnetic field. Again, this is gentle, gradual, and requires carrying additional equipment that adds mass to your spacecraft. Some proposals suggest sending the laser array information ahead of the spacecraft so that a similar installation could be built at the destination to decelerate the incoming probe. But this requires either that an advanced civilization already exists at the target star, unlikely and unverifiable until you arrive, or that we send automated construction equipment ahead that builds the laser array before the main spacecraft arrives. That requires two missions. First, slower automated constructors that take centuries to reach the destination, then the faster crewed mission decades later. We've just doubled the complexity and stretched the timeline even further. Let's assume somehow you manage to enter orbit around Proxima Centauri. Now you face an environment fundamentally different from anything in our solar system. Proxima Centauri is a red dwarf, about 1/8 the Sun's mass, and far cooler. It bathes its planets in a dim, reddish light that seems almost dark compared to the brilliant illumination we enjoy from our yellow Sun. Any planet in the habitable zone where liquid water could exist orbits very close to the star, completing its year in just 11 days for Proxima Centauri b. Red dwarfs are also violently active. Despite their small size and dim appearance, they produce powerful stellar flares, sudden eruptions that release enormous amounts of X-rays and ultraviolet radiation. Proxima Centauri is known to flare frequently, sometimes increasing its brightness by several times for minutes or hours. These flares bombard nearby planets with radiation far more intense than anything Earth experiences. Any atmosphere would be gradually stripped away over millions of years. The surface would be scoured by radiation during each flare event. If Proxima Centauri b, the potentially Earth-like exoplanet discovered in 2016, actually exists in the habitable zone and retains an atmosphere, it likely faces one side constantly toward the star, a state called tidal locking, similar to how the Moon always shows the same face to Earth. One hemisphere would experience eternal day under a dim red sun, while the other endures endless night. The temperature gradients would drive fierce winds, circulating heat from the day side to the night side. If life exists there, it evolved under conditions radically different from Earth's stable, sun-drenched environment. Exploring such a world would require equipment designed for extreme radiation environments, extreme temperature variations, and potentially fierce atmospheric conditions. The crew couldn't simply land and begin exploring like Apollo astronauts on the Moon. They'd need heavily shielded habitats, protective suits far more robust than anything currently designed, and would live under constant threat from the star's unpredictable flares. And here's something that should give us deep pause. We've been discussing this journey as if reaching the destination were the end goal, but for human crews, it's not. At some point, they either need to return home or accept that they're permanent exiles, that Earth is forever lost to them, except as a dim point of light in an alien sky. A return journey requires either carrying enough fuel for the return trip, multiplying all our earlier problems, or somehow manufacturing fuel and constructing a new spacecraft at the destination using local resources. That's generations beyond our current capabilities, even here on Earth, with our full industrial infrastructure. Expecting a small crew to build an interstellar spacecraft from scratch on an alien world verges on fantasy. More realistically, any crewed mission to another star would be a one-way colonization effort. The crew and their descendants would need to establish a permanent, self-sustaining settlement. This means not just surviving, but building an entire civilization from whatever they can bring and whatever resources they find. They'd need to grow food, manufacture tools, extract raw materials, refine them, fabricate complex machinery, maintain computer systems, and pass knowledge to subsequent generations, all while dealing with an alien environment that might be hostile in ways we can't anticipate. Consider the history of human colonization on Earth. Every successful colony had several advantages. They arrived in environments where humans could breathe the air, where water existed in drinkable form, where edible plants and animals were available, where materials for shelter and tools were accessible. Even with these advantages, many colonies failed. Roanoke vanished. Jamestown nearly starved. Antarctica remains permanently dependent on resupply from the outside world despite a century of exploration and the relatively short distance from other continents. An interstellar colony would have none of these advantages. The atmosphere, if it exists, is probably unbreathable, too much carbon dioxide, wrong oxygen levels, possibly toxic compounds. Water might exist but could be locked in ice or contaminated with minerals. No native life means no ready source of food. Everything must be grown from earth seeds and livestock, assuming you can create the right soil conditions and protect crops from alien environmental hazards. You're essentially trying to build and maintain a completely artificial Earth-like environment inside habitats, potentially forever, while gradually expanding your capacity to utilize local resources. The minimum viable population for long-term genetic health is debated, but estimates generally suggest at least several hundred individuals to avoid excessive inbreeding over multiple generations. That's several hundred people you need to transport across light years with all of the life support, space, and supplies that entails. The spacecraft would need to be enormous, the energy requirements astronomical, the cost beyond anything humanity has ever attempted. And you're sending these hundreds of people on a one-way journey, asking them to leave behind everything they know, everyone they love who doesn't come with them, and their entire world, betting their lives and their children's lives on succeeding in one of the most difficult endeavors imaginable. Who would volunteer for such a mission? What kind of person accepts permanent exile to an alien world they'll reach only after decades in space, with enormous risks of failure at every stage, knowing they'll never see Earth again, never walk in a forest, never swim in an ocean, never experience anything familiar except what they bring with them in their tiny spacecraft. Perhaps pioneers exist who would make that choice. Perhaps the promise of being humanity's first interstellar colonists, of ensuring that our species becomes multistellar, would be enough. But the mission would require not just technical excellence but psychological profiles, unlike anything we typically select for in astronauts, people willing to embrace permanent separation from their species' homeworld. And even if the colony succeeds, even if they establish a thriving settlement on Proxima Centauri b, or construct habitats in orbit around the star, they would be effectively cut off from Earth. Communication at light speed means messages take over 4 years each way. Any request for help, any question about how to solve a technical problem, any cultural exchange or scientific collaboration operates on timescales measured in years or decades. The Proxima colony would develop independently, creating their own culture, potentially their own language variations, their own technologies adapted to local conditions. Within a few generations, they might be more alien to Earth humans than any culture that has ever existed on our planet. There's a deeper philosophical question lurking beneath all these technical challenges, one that goes to the heart of why we dream of reaching the stars in the first place. Why do we feel this pull toward interstellar exploration when the obstacles are so overwhelming? What drives this yearning to transcend our cosmic neighborhood? Part of it is simply our nature as a curious, exploratory species. Humans have always pushed beyond known boundaries. Our ancestors left Africa and spread across every continent. We crossed vast oceans in fragile boats, climbed the highest mountains, descended to the deepest ocean trenches, and eventually left our planet entirely. Each frontier seemed impossible until we conquered it. From this perspective, interstellar travel is simply the next horizon, and the difficulties are just problems waiting for solutions. But there's a crucial difference between those historical frontiers and the interstellar challenge. Previous explorations pushed against technological and geographical barriers, but they didn't confront fundamental physical laws. Building a better ship, developing navigation tools, improving survival equipment, these were engineering problems. Difficult, yes, but solvable through innovation and persistence. The speed of light, however, isn't an engineering constraint. It's woven into the mathematical structure of space-time itself. You can't innovate your way around it any more than you can innovate a square circle or a four-sided triangle. Let me share something that really crystallizes this dilemma. Recent work by physicists examining warp drive concepts, theoretical methods of faster-than-light travel that would work by warping space-time itself rather than moving through it, consistently reaches the same conclusion. Even the most optimistic models require either exotic matter with negative energy density that may not exist, or energy equivalent to the mass of entire planets or stars. One recent analysis suggested that even a highly optimized warp drive would require energy equivalent to roughly the mass of Jupiter, converted entirely to energy via Einstein's equation. That's almost 2 times 10 to the 27th power kilograms, a number so large it's essentially meaningless in human terms. For context, the total energy humanity currently produces in an entire year is roughly 600 exajoules, or 6 times 10 to the 20th power joules. The energy to warp spacetime for faster-than-light travel would require roughly 10 to the 42nd power joules. That's more energy than humanity has produced in all of recorded history, multiplied by trillions. Even if we somehow develop the technology to manipulate space-time, which remains purely theoretical, the energy requirements place it forever beyond practical reach. This is what makes interstellar travel fundamentally different from previous human endeavors. We're not just facing engineering challenges that future technology might overcome. We're confronting the basic architecture of reality, and that architecture seems deliberately designed to keep us confined to our local neighborhood. Some scientists have proposed what they call the interstellar distance filter, the idea that the vast gulfs between stars might be a deliberate feature of the universe's structure, not a bug. In discussions about the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial civilizations and the complete lack of evidence for them, interstellar distances offer a compelling explanation. Perhaps intelligent life arises frequently in the universe, but the sheer impossibility of crossing interstellar space keeps each civilization isolated on their home world, or at best their home star system. The galaxy could be teeming with civilizations, each one alone, each one looking up at the stars and wondering why the universe seems so empty. This isolation might actually serve an important purpose. It prevents conflicts between civilizations at different technological levels. It ensures that each species must solve their own problems rather than depending on rescue or conquest from outside. It keeps the consequences of our choices local. We can't flee to new star systems when we've exhausted our home world's resources or damaged its environment. We must learn to live sustainably on the world we have because there's nowhere else to go. But this feels deeply unsatisfying to the human spirit. We look at the night sky and see hundreds of billions of stars in our galaxy alone, with potentially billions of Earth-like planets. And the thought that we might never reach any of them contradicts something fundamental in our nature. We are stardust that has become aware of itself, atoms forged in ancient supernovae that have organized into structures capable of contemplating their own origins. The cosmos made us, and we long to explore it in return. Perhaps that's why proposals for interstellar missions continue despite the overwhelming obstacles. In 2026, NASA's selection of the swarming Proxima Centauri concept for continued study represents hope that incremental progress is possible. Maybe we can't send humans to the stars in our lifetimes, or in any lifetime, but perhaps we can send robotic emissaries that extend our senses and satisfy some of our curiosity. It's not the same as human exploration, but it's something. Yet even these modest robotic missions face daunting challenges. The Breakthrough Starshot initiative, despite its prestigious backers and bold vision, has largely faded after revealing that the costs would vastly exceed initial estimates. The required technology, gigawatt-scale laser arrays, gram-scale spacecraft surviving 40,000 G accelerations, ultra-thin sails enduring 100 gigawatts of focused laser power, remains theoretical. Prototypes exist at small scales, but scaling up to functional systems requires breakthroughs in multiple fields simultaneously, along with funding measured in tens or hundreds of billions of dollars. And even if successful, what do we gain? Pictures of alien worlds taken during brief flybys, measurements of magnetic fields, spectroscopic analysis of any atmospheres present, perhaps confirmation of life's presence if we're extraordinarily fortunate. Valuable scientific data, certainly, and inspiring achievements that would capture human imagination. But we're still not there. We're looking through a tiny window at worlds we can never touch, analyzing data from environments we can never experience directly. There's a poignant tragedy in this situation. We live in a universe of incomprehensible vastness and beauty. Our galaxy alone contains somewhere between 100 billion and 400 billion stars. Many, perhaps most, host planetary systems. Some unknown fraction of those planets exist in habitable zones where liquid water could exist. If even a tiny percentage harbor life, and an even tinier percentage develop intelligence, the galaxy should be alive with civilizations, with cultures and technologies and philosophies we can't begin to imagine. But the distances are simply too vast. Light itself, the fastest thing in the universe, takes 100,000 years to cross our galaxy. A radio message sent to a star just 100 light-years away wouldn't receive a reply for 200 years. Meaningful communication, let alone travel, operates on timescales that exceed human lifespans, civilizational lifespans, perhaps even species lifespans. We might share the galaxy with countless other intelligences, all of us alone, all of us isolated by the tyranny of distance and the speed limit of light. Some find comfort in the idea that perhaps eventually, over timescales measured in millennia or longer, humanity might spread slowly through the galaxy. Generation ships taking thousands of years per journey, each new colony eventually spawning more missions to more distant stars, a gradual expansion that might eventually result in human presence throughout our local galactic neighborhood. Over millions of years, this slow diffusion could potentially colonize a significant portion of the galaxy, but this scenario requires sustained commitment across time periods that dwarf recorded history. It requires each generation to invest enormous resources in missions that won't succeed for hundreds of generations. It requires that human civilization, or whatever we evolve into, remains stable and committed to this project across epochs during which species typically go extinct or evolve into something unrecognizable. And it still doesn't solve the fundamental problem. Even if our distant descendants spread among the stars, you, personally, reading this now, will never leave our solar system. The stars will remain points of light in your sky, beautiful but forever unreachable. Let me take you deeper into a specific scenario that illustrates just how fundamentally different interstellar travel is from anything else we've attempted. Imagine we decided tomorrow, as a unified human civilization, to make reaching Proxima Centauri our absolute priority. We dedicate the resources of the entire planet to this goal. What would actually happen? First, we'd need to choose our approach. Let's say we select fusion propulsion as the most plausible technology. It's theoretically possible even if we haven't achieved it yet, and it doesn't require exotic physics like antimatter or laser arrays covering entire continents. We commit to building the International Thermonuclear Experimental Reactor and its successors on an accelerated timeline. Instead of the current cautious, decades-long development process, we pour unlimited funding into fusion research. Under extraordinarily optimistic assumptions, we might achieve working fusion reactors within 20 to 30 years. Then we'd need another generation to miniaturize the technology, make it reliable enough for spaceflight, and develop the engineering to convert fusion energy into thrust efficiently. We're now 50 to 60 years into the project, and we haven't yet built the actual spacecraft. We've just developed the propulsion technology. The spacecraft itself would be colossal. For a crew of, let's say conservatively, 100 people, enough genetic diversity for a viable colony, you'd need habitation space, life support systems, recycling air and water with near-perfect efficiency, radiation shielding, potentially including meters, thick layers of water and metal, food production facilities with hydroponic gardens, equipment for manufacturing, spare parts and tools, comprehensive medical facilities including surgery suites and pharmaceutical production, power generation beyond the fusion drive itself, communication arrays, scientific instruments, landers for exploring the destination system, computing systems with massive redundancy, and storage for everything needed to establish a colony. Engineers estimate such a vessel would mass at least tens of thousands of tons, possibly hundreds of thousands. For comparison, the International Space Station masses about 420 tons and cost roughly $150 billion to build and required over 40 launches to assemble in orbit. Our interstellar arc would be hundreds of times larger, far more complex, and couldn't be assembled piece by piece over time. Every component must work flawlessly from departure because there's no opportunity for fixes once you leave Earth's vicinity. The construction would likely occur in orbit, requiring an infrastructure expansion beyond anything we've built. Thousands of launches carrying materials, components, and construction equipment. Orbital shipyards staffed by hundreds or thousands of workers. Assembly operations taking decades. We're now perhaps 80 to 100 years into the project, and we still haven't launched. Meanwhile, you'd need to select and train the crew. Who do you choose? The mission will last at minimum 40 to 50 years one way, meaning most crew members will die before arrival unless we develop life extension technologies or hibernation. Do you select young people in their 20s, knowing they'll reach their destination in their 70s or 80s, likely too elderly to do the hard physical work of establishing a colony? Do you plan for multiple generations born aboard the ship, accepting that most crew members will be people who never chose this mission, who were born into it? The psychological screening would be crucial. These people must function in close quarters, under stress, isolated from Earth for decades or their entire lives. They must be technically skilled enough to maintain incredibly complex systems, adaptable enough to handle unexpected problems, and psychologically resilient enough to not break down under the strain. Finding 100 people who meet all these criteria would be extraordinarily difficult. Training them to operate and maintain every system aboard the spacecraft would take years. Let's say we succeed at everything so far. 120 years after the project began, we're finally ready to launch. The fusion drive ignites and the massive arc begins accelerating. To reach 10% of light speed, a relatively modest interstellar velocity, requires continuous acceleration for months or even years, depending on the efficiency of your drive. During this time, the crew experiences persistent thrust, perhaps equivalent to 1/10 of Earth's gravity. Not enough to feel normal, but enough to prevent the worst effects of weightlessness. Finally, the ship reaches cruising speed. The fusion drive shuts down and the crew experiences microgravity for the next several decades, unless the ship rotates to generate artificial gravity through centrifugal force. At 10% of light speed, the journey to Proxima Centauri takes roughly 42 years. Add the acceleration and deceleration phases, and you're looking at 50 years total. During those 50 years, everything must work perfectly. A single critical failure, life support malfunction, computer system crash, fusion reactor breakdown, could doom the entire mission. The crew must repair and maintain systems using only the resources they brought with them. If a crucial component fails and they don't have a spare, the mission fails. There's no calling for help, no rescue mission, no resupply. Let's assume incredible luck and competence. The ship survives the journey. 50 years after departure, 170 years after the project began, the Ark enters the Proxima Centauri system. The deceleration phase begins, using the last of the fusion fuel to slow down enough to enter orbit. The crew, now mostly elderly survivors of the launch plus middle-aged individuals born during transit, begins surveying the system. What do they find? Proxima Centauri b, if it exists and is detectable, orbits in the star's habitable zone, but is likely tidally locked, bombarded by stellar flares, and possibly lacks any atmosphere. Even in the best-case scenario where it retains an atmosphere, it's almost certainly unbreathable. The planet might be sterile, scoured by radiation. Or it might harbor life, but life adapted to that harsh environment, possibly microbial, possibly incompatible with Earth biochemistry, potentially hazardous to humans. The crew must make a choice. Do they attempt to land and establish a surface colony on a world that might be inhospitable? Do they construct orbital habitats using resources mined from asteroids or moons in the system? Do they accept that the destination isn't suitable and somehow attempt to travel onward to another system, extending their journey by additional decades or centuries? Remember, these are people who've spent 50 years traveling, who are isolated from Earth by over 4 light years, who cannot receive meaningful help or guidance because any message takes 4.24 years to arrive and another 4.24 years to receive a reply. By the time a message sent at arrival receives a response, nearly 9 years have passed. The situation has evolved, conditions have changed, and the response might be irrelevant. Now let's add a final sobering detail. While the Ark was traveling for 50 years at 10% of light speed, Earth didn't stand still. Technology continued advancing. Perhaps 20 years after the Ark launched, humanity developed more efficient fusion drives. 30 years after launch, someone cracked the engineering challenges of antimatter storage, allowing ships to reach 25% of light speed. A second mission launches 70 years after the first Ark departed, using this superior technology. It arrives at Proxima Centauri in just 20 years. The crew of the original Ark, who sacrificed 50 years of their lives, who buried friends and family in space, who endured decades of isolation and hardship, arrived to find that a newer, faster ship got there first. Their historic achievement is overshadowed. The galaxy's first interstellar colonists are greeted not by the empty system they expected, but by a settlement already established by people who left Earth decades after they did. This scenario, called the weight equation, or interstellar weight calculation, poses a genuine dilemma for interstellar travel. If technology continues improving, launching now means you might be overtaken by missions launched later with better technology. But if you wait for better technology, it might never be good enough, or someone else might launch first. At what point do you commit to a mission knowing that faster ships might overtake you? The mathematics of this problem are genuinely challenging. Some analyses suggest there's a point where technology improvement slows enough that launching makes sense. But if we're nowhere near the physical limits of propulsion, and given that the speed of light is still 10 times faster than our hypothetical 10% of light speed, we're clearly not, then waiting might always be the rational choice. Yet waiting indefinitely means never going at all. This creates a peculiar paradox. The rational approach might be to continuously improve technology without actually launching, always planning for the mission, but never executing it because waiting promises better results. But taken to its logical conclusion, this means interstellar missions never happen despite continuous technological progress. There's another dimension to this challenge that we haven't fully explored yet: the economic reality of interstellar missions. We've discussed the physics, the engineering, the biology, and the psychology. But ultimately, someone has to pay for all of this, and the costs are staggering beyond anything humanity has ever attempted. Let's try to estimate the actual price tag of an interstellar mission. The International Space Station, our most expensive space project to date, cost approximately $150 billion spread across multiple nations over several decades. It weighs about 420 tons and operates in low Earth orbit, just 250 miles above our heads. Resupply missions arrive regularly. If something breaks, we can send replacement parts within months. Crew members rotate every 6 months, so no one experiences the extreme isolation and confinement of a multi-decade voyage. An interstellar arc would be orders of magnitude more complex, more massive, and more expensive. Conservative estimates suggest construction costs alone would exceed $1 trillion, possibly several trillion. That's $1,000 billion minimum, roughly the annual GDP of countries like Indonesia or the Netherlands. And that's just construction. Research and development to create the necessary technologies would cost hundreds of billions more. Training crews, building the orbital infrastructure to construct the ship, developing and testing life support systems. Each component adds billions to the total. We're talking about a project that would cost more than the Apollo program, the International Space Station, the Manhattan Project, and the construction of the interstate highway system combined. It would represent the single most expensive endeavor in human history, and unlike those projects, there's no immediate practical benefit. The Apollo program gave us telecommunications, satellite technology, weather forecasting, GPS, and materials science advances. The Manhattan Project, whatever its moral complications, ended a devastating war. The interstate highway system transformed American commerce and mobility. An interstellar mission offers none of these tangible returns. The crew wouldn't return within any sponsor's lifetime. Communication delays mean real-time collaboration is impossible. Any resources discovered at the destination are too far away to benefit Earth. The justification is purely scientific and philosophical, expanding human knowledge, ensuring our species becomes multi-stellar, satisfying our curiosity about the cosmos. These are noble goals, but convincing governments or private entities to invest trillions of dollars for philosophical satisfaction is extraordinarily difficult. Consider the political reality. Democracies operate on election cycles measured in 2 to 6 years. Politicians need to show results to voters before the next election. A project that won't show results for 150 years, from project inception to arrival at the destination, crosses multiple generations of politicians. none of whom will be in office to see success. The incentive is to cut funding and redirect it to projects with more immediate payoffs. Authoritarian governments might seem better positioned to commit to century-long projects, but they face their own challenges. Regimes change, priorities shift, and economic realities intrude. The Soviet Union began as a revolutionary state in 1917 and dissolved in 1991, a lifespan of 74 years. Even the most stable governments rarely maintain consistent priorities across multiple generations. Private funding seems equally unlikely. Billionaires occasionally fund ambitious space projects: Elon Musk's SpaceX, Jeff Bezos's Blue Origin, Richard Branson's Virgin Galactic, but these focus on near-term goals with potential returns on investment. Satellite launches generate revenue. Space tourism might become profitable. Mars colonization, if successful, could establish valuable infrastructure. But interstellar travel offers no plausible return on investment. It's pure expense with no financial upside, making it unattractive to anyone operating on capitalist principles. Some have proposed international collaborations, pooling resources from multiple nations to share the cost. The International Space Station demonstrates that such cooperation can work. But the ISS cost $150 billion shared among 15 nations. An interstellar arc costing trillions would require contributions from dozens of nations, and maintaining cooperation across the century plus timeline while navigating shifting geopolitical alliances seems nearly impossible. History offers few examples of international projects maintaining funding and focus across even decades, let alone centuries. There's also the opportunity cost to consider. Every dollar spent on interstellar travel is a dollar not spent on climate change mitigation, disease research, education, infrastructure, or space projects with nearer-term benefits. In a world where millions still lack clean water, adequate nutrition, and basic medical care, arguing that we should spend trillions to send people to another star system seems almost obscene. The ethical case becomes difficult to make when so many immediate human needs remain unmet. Yet there's a counter-argument. Humanity has always invested in projects that extend beyond immediate necessity. We build cathedrals that take centuries to complete. We fund pure mathematics research with no obvious application. We create art, music, and literature that serve no survival purpose. We send probes to Pluto and beyond simply to see what's there. These endeavors define us as more than merely survival-focused organisms. They represent our capacity for curiosity, creativity, and long-term thinking. An interstellar mission would be the ultimate expression of this impulse, not because it's practical, but because it represents the grandest aspiration humanity could pursue. It would be a statement that we value knowledge and exploration so highly that we're willing to invest resources across generations for goals that transcend individual lifetimes. It would be civilization building on the grandest possible scale, a project that could unite humanity around a common purpose larger than tribal, national, or ideological divisions. But inspiring as this vision might be, it doesn't change the economic reality. The money doesn't exist, the political will isn't there, and the technological barriers remain formidable. We're left with a peculiar situation where interstellar travel is possible in principle. No laws of physics absolutely forbid it, but impossible in practice due to the combined weight of engineering challenges, biological limitations, psychological factors, timescales, and economic costs. So where does this leave us? Are we truly trapped forever in our solar system, able to gaze at the stars but never reach them? Is humanity's destiny to remain confined to a single star, perhaps spreading through our local planetary system but never venturing further? The evidence suggests this might be the case, and we need to grapple with what that means for our species and our place in the cosmos. There's something profoundly humbling about confronting this limitation. We are, in cosmic terms, tiny creatures on a small planet orbiting an average star in an ordinary galaxy. The universe is unimaginably vast. Our observable universe contains perhaps 2 trillion galaxies, each with hundreds of billions of stars. The total number of planets likely numbers in the sextillions or septillions, and yet nearly all of it is forever beyond our reach. We can observe it, study it, understand it through mathematics and physics, but we can never physically visit the overwhelming majority of cosmic wonders. Perhaps this is as it should be. Perhaps the universe's vast scale serves to remind us of our smallness, while simultaneously inspiring awe at our ability to comprehend it despite our limitations. We are stardust, contemplating stars, conscious arrangements of atoms, pondering the cosmos that created us. We might never reach other stars physically, but through our telescopes, our mathematics, our imagination, we can reach them intellectually and spiritually. If this deep dive into the physics and practicalities of interstellar distances has left you wondering about the fundamental measurements of cosmic space, I have another video that explores this in detail. It's called How Long Would It Take Us to Travel 1 Light Year?, where we break down exactly what a light year means, put it in perspective with distances we're familiar with, and examine what various propulsion technologies could achieve over that staggering distance. It's a perfect companion to this discussion and really helps visualize the scale we're dealing with.